linear transformations or mapping between vectors. What does that mean? Let's say you have two vectors, vector u and vector v. Okay, so a function is defined as a mapping where for each member of the vector space v, then you will map that to a member of the vector space w. And if you don't remember what the vector space was, I uploaded a video for that. Last session we covered that too. By the definition, vector space is a space of vectors that for two operations, addition and multiplication, they are closed. Basically, any two members you choose, if you add or multiply by scalar, then you will get another member from the same set. So if you choose any constant or a scalar, and if you choose any member from the vector space V, the function or linear transformation map that member to a member from the vector space W. So it's called linear if the transformation holds these properties. What are those properties? If you transform the addition of two vectors, that's going to be equal to transformation of the first vector plus second vector, transformation of second vector. And if you transform a scalar multiplied by the vector, that would be equal to the multiplication of the scalar by the transformation of that vector. So by transformation, it can be any operation. We can mathematically write it down. We can define it. We can go further, discuss it. But let's, for now, accept this definition of the linear transformation. So in other words, you can say that linear transformation preserves vector addition and scalar multiplication using these two equations. What are the examples? Some good examples of that is actually a matrix. So what is a matrix? Let's say you have a vector that belongs to Rn space, which means that it has n elements, and each element is going to be a real number, but there are n of them, and they are ordered. So in total, you have a vector. And let's say you have another vector. That vector, let's call it W. It has m dimension of m, belongs to Rm, which means that you have m R members that are ordered, and the total will be a vector double. So a transformation defined from Rn to Rm. So you remember this definition. So this is your first vector space. This is your second vector space. Now, let's say we want to define a transform that from Rn is going to map anything to the space of Rm. What is that? That can be represented by a matrix of m by n. That's the definition of matrix that it comes from. What does that mean? That means that I have a transformation. Its input is going to be Rn. Its output is going to be Rm. Tx is equal to transformation of the vector x is equal to a times x, where x, each of them belong to the Rn. Let's go deeper in matrices. Matrices as elements of m by n. So this matrix, often they are called by themselves from the space of Rm by n. What does that mean exactly? That means that a matrix can be defined by m rows and n columns, and each of them can be a real number. So in that fashion, you can say that Rm by n is the space of matrices that are m by n dimension. The way they look, they are looking an ordered array members, and they are ordered such that you have m columns and m rows. So what is this member? You look at the row number 2, you look at the column number 2, so that member is a 2 by 2. What is this member? So you look at the row, what is this row m? But you look at the column, what is this column n? So that's going to be A M N. And overall, you can write it in a compact way, A sub A J, where I can be any number from 1 to M, and J can be any number from 1 to N. This is a compact mathematical way of explaining matrices. If you say A belongs to the space M by N, or Mi by N, where A is a matrix, in a compact way, you can write it this way too. By English, here we have this expression, A belong M by R M by N means A is a matrix with M rows and N columns, and every entry of A is everything here. By mathematics, you can write it. What is that definition? What is that expression? So A is a matrix. Each of these elements we can call A sub ij, and they belong to the space M by N. So that means that I can be any number from 1 to M, or J can be any number from 1 to N, and each of those, any one you choose, is belonging to the real numbers set. So that's a concise way of defining what the matrix mathematically is. Let me ask a question, maybe engage the class a little more. So, okay, let's say I have this matrix. Okay, what should be these two numbers? So this matrix, how many columns it has? Two. So if you look at here, Rm meant a matrix space, a vector space, where you have matrices, where the number of rows were m, a number of columns were n. Okay, so here, this is a matrix. How many columns it has? It has two columns. Column 1, column 2. It has 3 rows. Row 1, 2, 3. So that means that here should be number of rows, which is 3, and here is number of column 2. So in this example, A belongs to this space. And that's the same thing that you see in homework. So in homework, you see all of them most likely were R3 or R2. But here you see matrix definition, which is slightly different. So I continue with matrix definition. What is matrix? Matrix is a rectangular array of numbers, okay, arranged in rows, where rows can be from I1 to M, and when where the columns can be any number from 1 to n. So this is column 1, 2, 3, 4, all the way to n. This is column 1, 2, row 1, 2, 3, 4, 5, all the way to n. Okay, so and this means that A belongs to a space that the dimensions are at the dimension is m by n. And this is the same as what you have seen before. For instance, if you say A belong to R, what does that mean? That means that X could be 1, could be 2, could be 1 minus 1.4, it could be minus 2. All these numbers are real numbers. So when you have instead X belong to R2, what did that mean? That means that you could have X is equal to 1, 2, X could be 0.5 and minus 1, all the way, any possible numbers. Okay, so if you had someone told you X belong to N2, what does that mean? That means that X could be natural number, and it can be a vector 1, 2, 4, 5, all the way. And then the matrix is an extension of all these ideas, where you can say X belong to Rm by n. So it can be an array of m rows and n columns, where each member of those that array is a real number. So visualization, as we discussed, we can have columns, multiple rows, and each of them is going to give you one element. So what is the transpose of matrix? So the transpose of matrix is that if you see any member, so let's say A before transpose is the matrix, then A transpose, in A transpose, you switch the columns with the rows and rows with the columns of the new matrix. What does that mean? That means that if you had, for instance, A equal to 1 and 2, then A transpose would be, here is row 1, right? And column 1. So in new matrix, row 1 and column 1, it would be 1 still. But for this one, it was row 2 and column 1. So for the new matrix, instead of row 1, row 2, you will have column 2. And instead of column 1, you will have row 1. So that's 2 is going to come here. So that's the transpose. In that definition, you can summarize by a transpose is defined that if you have a matrix of A by n, m by n, then the transpose for each row number and column number, you switch them. So that's the definition of the transpose. So this is another example. Let's say it's A. So what is A transpose? So this is column 1. So if you have here, so if you have column 1, row 1, row 2, column 1, column 2, column 3. And so if you want to transpose A, you had 2 rows. So for the transpose, you should have 2 columns now. You had 3 columns. Now for the transpose, you should have 3 rows. And you have to switch the column and vector in the in the transpose. So if you had 1 and 1, you will have 1 and 1 for column and row number. But if you had row 1 and column 2 in the transpose, you should have row 2 and column 1. So then B, from there it comes here. For instance, if you had row 2 and column 3, in the transpose, these 3 and 2 switches. They switch. So what it means is that in the transpose, if instead of column 3, it would be row 3. And if also instead of having row 2, it should go somewhere that 2 associated with the column. So in that fashion, F goes here where the row is 3 and column 2 instead of row 2, column 3. So that's how all the elements gonna transpose. That's how you do transpose. So for the matrix addition, let A and B belong to Rm by n. Okay. So then we want to define what would be the addition of those matrices. So for the addition, A plus B, for each element, for their row and their column, they add together, and that would be the addition of 2 matrices. What does that mean? That means that if you add these 2 matrices, so if you want to add, first they have to have the same dimension. This is 3 column, this is 3 column, this is 2 row, this is 2 row. So the dimensions match. So how do you add? Then what you add is that you see 1, 1, column 1, row 1, these 2 add together, and that becomes here. For row 1 and column 2, here you have 2 in the same, for the same position, you have 8 here. You add these 2 and then you write it here. So you repeat all these operations, and in total you will get the addition of 2 matrices as shown here, which is element wise you have to add all of them. All this mathematically is described by this equation here, where C sub ij is equal to A sub ij plus B sub ij. What does that mean? That means that if you have A and B belong to Rm and n, here it means that A sub ij, I and j can be any number from 1 to m, and j can be any number from 1 to n. And for each position of the matrix, you add them element-wise to get the addition matrix. Multiplication. If you have a scalar belong to R, a real number, and if you have matrix belong to Rm by n, which means that a matrix of m rows and n columns, then Ca again would be a matrix with the same dimension, and for that each entry of the matrix is going to be multiplied by C. That's it. So this is mathematically can be written by this expression, which means that Ca is a matrix by itself. So each of its entries, I sub j, is equal to the real number times the entry of A sub ij. So now if we want to write it, expand it, write it in terms of numbers, that's an example. So for instance, here is your A, here is your C. So 3 times that A is going to be a matrix by itself. Let's call it matrix B. And for that matrix, all these entries are going to be multiplied by C, by 3. So you have elements, each entry is multiplied by this 3 here, but by the number 3 here, and here you will get 3 by 2, 6, 3 by minus 1, minus 3, 3 by 0, 0, 3 by 4, 12. What is matrix products? So the matrix products, so you learn what the matrix is. It's a square of arrays that belongs to a space Rm by n. And let's say you have another square of arrays belongs to a space Rn by p, right? And then you want to multiply them. So you want to define what their product is. Their product is different from their multiple way of producing matrices. Here, the main definition is here that the product only if this holds, which means that this n is matching this n here. So here is you have m by n, here you should have n by another number. You cannot have here another number instead of, in terms of dimension of b. Otherwise, the product is not defined actually. So in that case, AB is a matrix of m by p. So note that this n canceled. So you had m by n matrix multiplied by n by p matrix, and the product became m by p. So n is basically eliminated. So that's how you memorize easily. Can I multiply these two matrices together or not? If you wanted to multiply a times b, this is the definition. This is the mathematical definition of the product. It looks complicated. I explain first what it means. Then we expand it, which means that we show in expansion by calculation by hand what it means. So this is basically concise way of explaining that. So if you have A by B, each entry of them, which means A, B sub ij, is equal to this summation, where A sub ik is multiplied by B sub kj, and the k can be any number from 1 to n. So note that this is for one single entry. I here should run from 1 to m, and j here should run from 1 to p. Why? Because the product will have a dimension of r m by p. So now this is, you can think about that, what it means. You can expand it by the series that you learn. But if you wanted to, in practice, apply that, this is how it's applied. So maybe in practice, you can memorize it easier. Someone may find this is easier way of memorizing that. Someone may find this is easier way of memorizing that. So in practice, what happens, what it means is that if you multiply two matrices, this is my matrix A, this is my matrix B. So if you want to multiply for each of these entries, okay? So what is this entry? This entry is row 1, column 1. What is this entry? Is row 2, column 1, okay? So for row column 1, you have to calculate the dot product of a vector that comprises the row 1 of matrix 1 and column 1 of matrix 2. For this entry, which is 2, 1, you have to calculate the dot product of row 2 and column 1 now. For the entry 1 by 2, now you have to calculate dot product of row 1 by column 2. All the way to 2 by 2, you should calculate the dot product of row 2 by column 2. So I clean it. So for understanding it better, here is with color, so you can remember what was what. So the dot product of, let's say, this column by this column is this element times this element plus this element times this element, right? So you have it red from row 1, B from row 1, and E from column 1, and G from column 1, 2, okay? So in another fashion, and also you can see for 2 by 2. So for 2 by 2, you have the first member for row 2, the second member for row 2, and they are multiplied by first member, second member by column 2, first member by column 2. Instead of seeing all these numbers, explain one more time, one more way. Let's say I want to compute this dot product. It is matrix product. What is this entry? This entry is row 1, column 1. What does that mean? I have to go look at the first matrix, row 1, take it out. I have to look at second matrix, column 1, and take that thing out too, and then multiply those two together and write it here. I repeat, if I wanted to, let's say, compute the dot product where I have row 2 and column 1, right? So what I will have to do, because it's row 2, first I will go to the first matrix. I look at this row 2, take it out. Then I will go to the second matrix, column 1. Take that column 1 out and multiply those together and put it the product here. So you go all the way for all these ones and compute them the product of the two matrices. They are similar to transpose of the matrices. However, you have like only one row or one column only. You want to remind one definition you want to learn is that what is a span? A spans spans of k vectors, means like if you have k vectors, if you can multiply them with any real numbers and add them together, it's going to generate a new vector. So how does that space look? How many vectors belong to that space? That's a span of these vectors. So you wanted to learn what that definition is using a simple problem. There are some axioms for the first problem that's you were asked. What are the transpose of these matrices? So one of them, for instance, this is easy. So column, row 1, row 2, row 3, row 4, right? So all of them will become columns. So 1, 2, 3, 4, these are columns. And the column 1 become row 1. And then you have C, X, Y, 10. Okay, so this is one example for the transpose of vectors. So transpose of row vector, same thing. You have column 1, column 2, column 3, until column 5. All of them becomes rows, row 1 to 5. And you put them, the numbers here. Vector operations in Rn. I asked if these vector operations, what is the addition of these two? Can be done or not, right? So for some of them you cannot. Here you cannot because the dimensions do not match. This is dimension 2, this is dimension of 3. They don't match, so they cannot at all do that. But for those you can, element-wise you add them. For each element, for the entry of 1, 1, you add them and you put the entry of 1, 1. For entry of 1, 2, you add them, you put the entry of 1, 2. So all the way. So for clarification, if you are going to have the same, in addition, you are going to retain the space dimension. So for this entry, we have to add the corresponding entries for the two. And for this entry, you have to add the corresponding entries for the two vectors. Okay. Span of two vectors. A question is very simple. Assume we have these two vectors. Is this vector in their span or not? Okay, what was the span? The span was that C1 times 1 over 2 plus C2 times 2 over 4, where C1 and C2 belong R. Okay, so if that thing belongs to that span, it means that should be equal to 3 and 6. So all you have to do, you have to figure out if there exists any C1 and C2 belong to the real space that can satisfy this equation. If yes, then this is in the span of these two vectors. If no, then it's not. So how do you do that? You basically get two equations. C1 times plus C2 is equal to 3, and C1 times 2 plus C2 times 4 is equal to 6. Two equations, two unknown, you have to solve it. The answer is yes, probably.